Hello and welcome to this clip on buffer calculations. We'll start by doing a review of the Ka expression, how we use that to calculate the pH of a weak acid. Then we'll compare the standard calculation of the pH of weak acid with how we do it for a buffer solution. Then we'll move on to have a look at how the concentrations of the weak acid and the conjugate base in a buffer mixture can be manipulated so that the buffer maintains a specific pH value. And we'll look at a couple of examples of more applied and difficult examination questions on buffer calculations to round things off. In this clip we'll assume that you're already familiar with buffer action in itself, Ka calculations in weak acids and conjugate acid-base pairs. So to quickly review buffer action, a buffer mixture is a weak acid and its conjugate base which is able to resist small changes in pH. If acid is added in the form of H+ ions, they react with the conjugate base, A- in this example on the screen, and the equilibrium position shifts to the left. If OH- ions are added in the form of an alkali, they react with the dissociated H+ ions from the weak acid that are already there, and the equilibrium position shifts to the right. So the Ka expression is basically used because in the equation for the dissociation of a weak acid, it's in equilibrium, so not all of the HA will dissociate. So you can't assume that the concentration of your weak acid will be equal to the concentration of dissociated H+ ions. But it can be assumed that in monobasic acids, the dissociation gives H+ and the conjugate base A- in equal quantities in terms of moles. This makes the isolation of H+ concentration for the purposes of working out pH a lot easier. So if we want the concentration of H+ ions, we do the square root of Ka times the concentration of HA, which means we can then work out pH really easily by doing minus log of the concentration of hydrogen ions. So when we're doing the Ka expression for buffers, we can't make that assumption that H+ and A- concentrations are equimolar. A- tends to be in excess because, as you can see from the diagram, there's a large reservoir of our conjugate base. So we have to take a slightly different mathematical approach to identify the way of calculating the pH in buffers. We still use the pH equals minus log of the hydrogen ion concentration, but to get the hydrogen ion concentration, like I've just said, we have to take a slightly different approach. If we start with our normal Ka expression, the expression can now be rearranged like that. So Ka times the concentration of your weak acid equals H+ in concentration times that of the conjugate base. I'm keeping H+ concentration in red so you can see what I'm trying to isolate, which would give me this expression. The concentration of H+ in aqueous solution equals the Ka value times the concentration of the weak acid over the concentration of the conjugate base. And all three of those components of the equation would be given in the question to make this mathematically possible, which finally allows us to work out the pH of the buffer using the standard pH expression. Of course, it's no good being able to work out the pH of a buffer if we don't know how to actually control what pH that buffer will maintain for us. So looking at the Ka expression, and if we assume that Ka, concentration of HA, and the concentration of A- are all known, and we also take into account the fact the Ka value for our weak acid is fixed and unique, the only way to make sure that a certain pH is achieved is to manipulate the ratio of HA to A-. So if we go back to our original calculation for working out the H+ concentration of a buffer, remembering that the H+ is what we want to try and control, because it's the pH that we want to control, and also remembering that the Ka value is fixed and unique for each weak acid, the only thing that can be controlled easily is the ratio of HA concentration, or weak acid concentration, to the concentration of its conjugate base. And if you remember how we actually make a buffer, we can either make it by mixing the weak acid with an excess of its conjugate base, or we can mix the weak acid with a small amount of strong base that makes some of the weak acid turn into its conjugate base. Either way, provided we end up with the right HA aqueous divided by A minus aqueous, then we'll get the H plus value, the H plus concentration that we're looking for, and we'll therefore get the pH that we're looking for. So to control the pH at which a buffer maintains, we need to make sure that the concentration of the weak acid and its conjugate base are the same. If they're the same, that allows us to cancel them out in this equation. And therefore H plus in the H plus concentration rather will be the same as the Ka value. And the pH value will also be the same as the pKa value. So if the concentration of weak acid exceeds the concentration of conjugate base, then according to the expression, the H plus value, which is maintained, will increase. And the buffer will maintain a more acidic solution. If on the other hand it's the other way around and the concentration of the weak acid is less than the concentration of the conjugate base, then the H plus concentration value will decrease, and therefore the buffer will maintain a more alkaline solution. So in this way we can manipulate the ratio of weak acid to conjugate base concentration to control which particular pH the buffer will maintain for us. Another way of looking at it might be to consider Ka times a large number giving a larger H plus value, Ka times a smaller number giving a smaller H plus concentration. So the large number or the small number is obviously going to be dependent on the ratio of the weak acid concentration to the concentration of conjugate base. You might come across in your textbook, or perhaps in mark schemes, mention of the Henderson-Hasselbalch equation. It's an extension idea to our specification. It's not absolutely required, so you don't actually have to know it, but I'm including it as an alternative way of calculating buffer pH values. If I wasn't to talk about it, and you were then to go and look at a mark scheme for an exam question, for example, and you had mention of the Henderson-Hasselbalch equation, it might cause confusion if it hadn't been spoken about. So it's basically making use of the pKa value as opposed to the Ka value, and it uses logarithms. And if the concentration of your weak acid, HA, was equal to the concentration of your conjugate base, A minus, and what this would mean is that both of them would cancel each other out, like so. And therefore the log, or the logarithm of 1 equals 0. So that leaves us with pH equals pKa. So it's another rather neat way of proving that mathematically. But like I mentioned, it's an extension idea, and you don't have to know the Henderson-Hasselbalch equation. So I'm going to take you through a more applied and longer acid and bases and buffers question. In fact, this question had a little bit of notoriety back in 2012, I believe, when it came out. Sorry, 2011. It has a question at the end about a sweet, an imaginary sweet called Magic Tang, and the Magic Tang question actually was proved to be quite difficult to many people taking the paper at the time. So it's an interesting one to include, seeing as we're talking about more difficult buffer calculations. But it actually takes you through some quite useful ideas, so it's a useful exercise to try and work your way through it. So obviously it gives you some pKa values for a range of acids naturally found, because it tells you what they're found in: bark resin, vinegar, formed inside the body during metabolism, and obviously lactic acid from milk. So it starts you off with a very, very easy definition, what is meant by the term Bronsted-Lowry acid. I've decided to cover myself by saying it both ways, it's a proton donor, or you can say it releases H plus in aqueous solution. So pulling the page down a little bit, it says what is meant by the strength of an acid, and it says in your answer include an equation for one of the acids in table 4.1. Now if you were rushing this question it would be very easy to miss that part out, so you can see quite clearly it's a 2-mark answer. So they require you to not just explain what the strength of an acid is, but to also say, using an equation to support what you're talking about. And because it's obviously the simplest out of all the acids that are there, I'm going to go for ethanoic acid as my acid of choice. So it's the amount or the extent to which an acid dissociates or ionizes to give H plus aqueous. And I also put down the equation for the dissociation, the equilibrium for the dissociation of ethanoic acid. So the next question asks you to place the 4 acids in table 4.1 in order of increasing strength. So what you've got to remember here is that the relationship between pKa value and strength. So you've got to remember that the pKa value, the smaller the pKa value, the stronger the acid. So if we go back to the table and have a look, we can use the pKa values to assign an order. So starting with the weakest being ethanoic acid, and then we've got benzoic acid is the next one, next strongest. So the second strongest will then be lactic acid, and the strongest of them all will be pyruvic acid. And we can write it in like that. So let's bring the page down and have a look at the next part of the question. So this question is obviously about conjugate acid-base pairs. And what you've got to remember about conjugate acid-base pairs is that they interconvert by the transfer of a proton. So if you've got 2 acids reacting with each other, that might sound odd to start with, but if you think about it, the previous part of the question actually asked you to rate the acids or place them in order of increasing strength. So the stronger acid will take the role of acid, the weaker acid will take the role of base. So therefore, as C6H5COOH is weaker than CH3CHOHCOOH, what happens is that the benzoic acid on the left receives a proton from the lactic acid on the right, and therefore you get C6H5COOH2+ and CH3CHOHCOO-. 2 rather strange looking species, I give you that, but this is an applied question like we said, so it's giving you another unusual situation to see if you can handle it. So let's go on to the next part of the question now, over the page. So in this part of the question it refers to pyruvic acid. Now obviously, because this is a video clip, it's a bit tricky to go back and get the equation for pyruvic acid, or the formula for it, so I popped the formula at the top of the screen for your convenience. So it asks you to write an equation for the reaction between aqueous pyruvic acid and calcium hydroxide. So remember the mole ratio here. Calcium is a 2+ ion, so therefore it requires 2 pyruvate ions to react with it. And because it's an acid reacting with an alkali, in ionic terms it's simply H+ reacting with OH-. So that gives you an ionic equation that simply says H+ and OH- giving you H2O. So the next part of the question is a pH calculation, but it's actually saying the pH of an acid solution can be calculated from its pKa value. Now again, you've had the pKa value for pyruvic acid previously supplied, so I'll pop that on the screen here again so you can get started on this. So now that we have the value, the pKa value for pyruvic acid is 2.39, we can work out its Ka value. That would be a good start. which gives you 4.07 times 10 to the minus 3. Now I don't have to put moles per decimeter to the minus 3 in, but because it carries a unit, I always like to do that. That's just a personal preference. So the next thing to do is to start to look at the data we now have, so we can start to put it into the Ka expression. So remembering that in weak acids, the concentration of H plus and the conjugate base, A minus, are the same, that means we can make an assumption that H plus squared is going to be divided by 0.0150, which is the concentration of our pyruvic acid. So that allows us to work out the concentration of H plus by doing the square root of 4.07 times 10 to the minus 3 times 0.0150. So moving the page down slightly to make some room, we can work out that the concentration of hydrogen ions is 0.00782. And if we put that into the pH calculation, minus log 0.00782, that gives us a pH value of 2.11. So let's now go on to the next page of the question. So it tells us that oxalic acid, systematic name ethane dioic acid, is present in the leaves of rhubarb plants, and it has two dissociations with two different pKa's, meaning it must have two hydrogen atoms present that dissociate as H plus ions. So the structure must be basically two carboxylic acid groups joined directly to each other. Taking the name ethane dioic acid, this shouldn't be too difficult to work out. So looking at the next question, it asks you to predict the equations that give rise to each dissociation. Now you've got a dibasic acid, so the first dissociation will involve H plus coming off a neutral molecule. That's an easier process than H plus coming off a negatively charged ion, which would be the second dissociation. So because the first dissociation is easier, that means it'll be more likely that higher amounts of H plus will come off in the first dissociation. So therefore the first dissociation will have a smaller pKa value. If you remember earlier on in the question, you were asked to rate 4 acids according to their strength based on their pKa values, and we had to use the idea that smaller pKa values meant a stronger acid. A stronger acid means more H plus is released. So I've put down the two dissociations, the two equations, and you can possibly see what I'm talking about a bit further down. Next to the equation, the second equation, where the pKa value is higher, therefore it's a weaker acid, it's harder to release H plus because you're asking it to come off something that's already negatively charged. And therefore the attraction between the negatively charged ion and the hydrogen will make sure it doesn't come off quite so easily. So the second dissociation will have a larger pKa value, being a weaker acid, and the first dissociation will have a smaller pKa value, being a stronger acid. So let's now look at the final part of the question. It says, the magic tang in many sweets is obtained by the use of acid buffers. A sweet manufacturer carried out tasting tests with consumers and identified the acid taste that gives the magic tang to a sweet. And the manufacturer was convinced that the magic tang would give the company a competitive edge, so he asked the chemists to find the chemicals needed to generate that taste that the consumers liked. And the chemists identified that a pH of 3.55 was required. So we have to develop a buffer at that particular pH. So what we've got to do is go back to the table and use the pKa values to try and work out which of the acids would be the acid you'd need, because they're asking you to deduce the chemicals, which is essentially which acid and conjugate base combination. So essentially what they want you to do when they want you to calculate the relative concentrations is what is the ratio of the weak acid concentration to its conjugate base concentration required to maintain pH 3.55. And the third question is asking you to consider, is it just the pH of the sweet which creates the tangy taste, or could there be something else that's also contributing? So let's turn the page over to the answer section and see what we can come up with. So just giving you a quick data reminder to save us going back in the clip to try and find the data from the sheet. And just reminding you that we need a pH of 3.55. So also remembering the buffer works most effectively if the pH is equal to the pKa. The closest pKa value that will give you a pH of 3.55 is lactic acid. So we're looking at something like lactic acid and a suitable lactate salt. For example, lactic acid and sodium lactate would be good examples for our buffer mixture. So let's now work out suitable concentrations. You can use the required pH to work out the hydrogen ion concentration by doing 10 to the minus pH, in other words 10 to the minus 3.55, which gives you 2.82 times 10 to the minus 4, and like I've said before, I always like to put the units in. And remembering that the Ka value is the same as 10 to the minus pKa, so the Ka value this time for lactic acid is 10 to the minus 3.86, giving you 1.38 times 10 to the minus 4 moles per decimeter to the minus 3. So let's bring the page down a little bit to finish the calculation off. So we can rearrange the Ka expression for a weak acid to work out the ratio of HA concentration to A minus concentration. In other words, what we've got highlighted. So if we bring the page down a little bit more, so if we take A minus concentration over HA concentration from the highlighted part in red, and we take the Ka and hydrogen ion concentrations that we calculated earlier, from this expression this allows us to assume that they're equal to each other. So Ka is equal to A minus, and hydrogen ion concentration is equal to the concentration of my weak acid. So this gives us a value of 0.489. The final part of the question asked us to comment on the validity of the idea that the pH of the sweet created the magic tang taste. Now obviously you could say that the magic tang could come from other chemicals in the sweet, and the buffer itself might also happen to have the magic tang. Both of those are valid things to say. So now let's have a quick whiz through the mark scheme to see how we did. So we got the idea of a proton donor and the amount of dissociation. We happen to choose ethanoic acid. We got the order in the correct way, and we got both of the species in the conjugate acid-base pairings. But it's a 1-mark question, so you've got to have both of them. Now I've highlighted the fact that it says don't allow HA giving you H plus plus A minus. It's because you're actually given the 4 acids that you have to put the specific acid in. So don't use things like HA going to H plus and A minus if you're actually given the acid. But we didn't do that, so we didn't lose a mark. We got the correct mole ratios in our equation for the neutralization of pyruvic acid with calcium hydroxide. Interesting to note that pyruvic acid has to be used, and you actually have to say the correct formula. Now it's interesting that they don't allow you to put the charges for the pyruvic acid, sorry, the pyruvate ion in if you don't put Ca2+. In other words, the charges must balance. So that's one to be careful of. So we got the correct ionic equation for neutralization, and we eventually got 2.11. so we can give ourselves 4 marks because we got that. Now it's always recommended that you put the workings in just in case you mess up somewhere, so that they can give you some method marks. You can see for yourself that there's method marks all the way through. But it does say that if you get 2.11, you get 4 marks. It's a bit of a gamble. If you don't put the working down and you end up getting the wrong answer, but the workings that you put, or the workings that you did on your calculator, some of them were okay. So just to be on the safe side, make sure you put the workings in. It doesn't cost you anything, and if anything, it guarantees the marks for the workings that you get right. So in this one we got the correct structure. It's interesting to note that they put in the actual bonds for the OH, but they let us put in OH without the bonds. And we also got the 2 dissociations in the correct order. So whizzing through the Magic Tang one, we worked out that it was lactic acid because we made sure that it was the one that had the pKa value closest to 3.55, because we were working out that pH equals pKa, because that's the situation where the buffer is most effective. Now we got 2.8 times 10 to the minus 4, or sorry, 2.82 times 10 to the minus 4, and we also got 1.38 times 10 to the minus 4, both giving moles per decimeter to the minus 3. Now the one we happened to use in the next marking point was this one, so we got that mark, and we got this one here. So we said that the Magic Tang could come from other chemicals, and I put down that the buffer might have the same taste. Either one of those is fine. So that gives us the full marks there. And there's also the Henderson-Hasselbalch equation, alternative way of doing it. You don't have to do this. As you can see from the mark scheme, there's 2 possible ways of doing it. And in the specification, this is an extension only. So I'm stressing that a second time. It's extension only. You don't have to know the Henderson-Hasselbalch equation. But if it's of interest to you, if let's say you're a double mathematician or taking maths at A level and you like using logs, then this could be one for you. So hopefully this has been a fairly useful clip taking you through some of the different ways buffer calculations could be examined. This particular question on Magic Tang was one that did challenge quite a lot of people when it first came out, but it just goes to show that it was quite well written, and it was obviously aimed towards the top end of the ability range, your sort of B's and A's, and I thought it might be good to try one of these types of questions because buffers do tend to be a more challenging topic for many people. So, thanks for your time, appreciate your patience, and if you have any questions, please do bring them into your teacher, or maybe come and see one of us in a subject extension at college. But for now, thank you and see you soon.